My name is Piotr, and I'm a machine learning engineer at Wave, a self-driving car company from London. Before building a self-driving car, you'll need to build a simulator. It enables safe and scalable development and evaluation of self-driving vehicles. But building a simulator is an expensive and time-consuming process. Imagine building a AAA video game that is almost indistinguishable from reality. Today, I'm going to tell you about neural radiance fields, a technology that enables building such simulator in a scalable and fully automatic way. Wave is a London headquartered startup pioneering in a scalable way to bring automated vehicles to the UK and beyond. We started in 2017, when much of the industry believed that AV has been solved or was about to be solved. The approach dominant at the time was based on the traditional robotics stack, an approach that we call AV 1.0. The approach focused heavily on HD maps and hand-coded rules, which can be time-consuming to build and brittle. Wave emerged at a similar time as the modern take to deep learning, and we were able to take a deep learning approach to autonomous vehicles. At Wave, we replaced the perception planning stack of AV 1.0 with a deep neural network. We rely on a lean sensor suite, camera, GPS, and radar, and focus on an approach that is commercially scalable and efficient. We've been building a unique AV 2.0 technology, leveraging ML to build an adaptable intelligence that enables any electric vehicle to drive autonomously, even in places it's never been to previously. Wave's AI driver learns to drive from expert driving, on-road testing, and simulation. One of the techniques that Wave uses is called imitation learning. With imitation learning, instead of carefully crafted set of rules, the goal is to learn to drive like you or me would, by imitating an expert or from experience. More formally, given an observation of the current state of the world through camera, GPS, and radar, the AI driver learns the action that a human expert would perform in the same situation. And in practice, this means our technology can be trained on vast amounts of data, and then it generalizes what it has learned to drive in any city. For example, once our technology learns the concept of how to safely navigate through a roundabout in London, it can perform the same maneuver in another city, like Cambridge, that differs from London in the road layout and driving culture. So our approach relies on vast quantities of data, and it's not always feasible to collect this data on road, which is why simulation is important to us. It enables efficient testing of our models at scale, as well as generating training data for edge case scenarios and safely testing our models in those scenarios. We are exploring various ways to use simulation to reap full benefits of it. We know building a simulation can be expensive, but we can also apply the AV 2.0 principles and build a simulator automatically from data. And this is where radiance fields come in. Radiance field is a function from a point in space x and view direction omega to color and opaqueness. It describes light passing through point x and heading in direction omega. Radiance field describes the way the light flows through space, and if we know that, then this is enough to render a 3D scene. And given a radiance field, we can then reconstruct a 2D image by marching along the virtual camera rays and sampling the field at each step. It is a pretty convenient representation, because with radiance field, we do not need to care about physical properties of the scene, what objects are there and what materials they're made of, and what is the source of light. Instead, we have a direct description of how the light flows, and that's all we need to render a new image. So, naively, radiance fields could be represented as a 5D tensor mapping to the RGB values and density. However, such representation is neither practical nor feasible, as it would be prohibitively expensive to use and store even for very small scenes, and we would not be able to represent a continuous field. But it turns out that neural networks are very good at compressing the radiance field. All that's needed to train a neural radiance field are images or video and camera poses. the precise position of the camera that took each picture. We then task the model with reconstructing the input images via ray marching, and a radiance field representation is learned implicitly. This is not so common application of neural networks, especially generative neural networks. A single network is trained to memorize a single 3D scene, and there is usually no generalization between scenes. If we want to reconstruct another scene, we will need to train a second network. And on the right-hand side of the slide, there is an animation of NeRF in training. It is not quite real-time, but pretty close. This small scenes trains on a commodity hardware in under 5 minutes using NeRF Studio. And the source data for it is about a 30-second video I took with my phone. And at the bottom of the vase here, I placed a lenticular lens. A postcard printed with a lenticular lens. So this is the kind of postcard that changes the images when you tilt the postcard. And this is done to illustrate the importance of the viewing direction component of Radiance field. Previous techniques for 3D reconstruction would struggle with reconstructing this object. However, NeRF is able to capture that pretty well. So at Wave, using NeRFs, we are building a new technology, a neural fleet, to complement our driving fleet. As you recall, with NeRFs, we can go from images or videos and camera poses to 3D scenes. And this is what you can see on the slides. On the left-hand side is a video of our expert driving through a street in London. And on the right-hand side is a NeRF, a 3D reconstruction that we created from this video. So how do we build our neural fleet at Wave? We leverage the driving data already collected by our fleet of human-operated vehicles over the past few years. We rely on the vast quantity of data and unpredictability of urban driving to provide us with interesting and varied driving scenarios that we can later reconstruct. And we have set up a pipeline to continuously process new data and add new NeRFs to the fleet automatically. Simulators have been a core technology for the development of self-driving cars, and at Wave we've also been working on a simulator already. So how does this new approach complement the existing work? Well, on the top of the slide you can see a traditional rendering simulation. With this kind of simulation, it is easy to create a novel scenario because we have full control over the simulation. We can control how the road layout works, we can control what dynamic agents are there present, and the appearance of agents and buildings. However, some effort is required to recreate an existing scenario, something that we've encountered on the road and want to test more extensively. And especially agent behavior is difficult to program to behave realistically. However, new methods for this are emerging. And finally, photorealistic rendering is expensive, requires very high quality assets that need to be created by artists, and expensive processes such as ray tracing. On the other hand, at the bottom you can see 3D reconstruction created using NeRFs. And by definition, simulations that use NeRFs are photorealistic, because NeRFs are photorealistic out of the box. So this gives us a low domain gap between real and simulated world. Again, by definition, using NeRFs, it is easy to recreate existing scenes, including agent behavior. And I will touch more on that later in the presentation. And finally, it is difficult to edit scenes with NeRFs. However, again, new methods are emerging every day. So what are the benefits of NeRFs specifically for Wave's approach? I'm going to present two distinct use cases. First, we use NeRFs to generate photorealistic examples to supplement our training data. And secondly, we have built a suite of benchmarks that provide reliable metrics to measure our model's performance. So, as you recall, one of the techniques that Waves uses for training ML models is called imitation learning. The objective of the ML algorithm is to learn how to drive from data, turning input state, in this particular example camera image, into action. This is what you see on the slide. We have an input image that will be the input to our neural network and a trajectory the label that the neural network will need to learn. The trajectory is a trajectory that an expert driver was following from this moment. To train a model, we can use behavioral cloning, a supervised learning approach to imitation learning that does not need to interact with the environment, which has many safety benefits for self-driving cars. However, behavioral cloning has the known problem that it might not generalize to unseen situations. For example, here if the car drifted into another lane, the model might not be able to merge back into the original trajectory, as this kind of demonstration is very rare in our datasets, because expert drivers do not tend to drift into the wrong lane. To solve this problem, we need more data. But this particular kind of data would be difficult or dangerous to collect. The solution is to generate additional training examples through data augmentation, by perturbing the trajectory and generating a corrective actions that merges back to the original trajectory. And let's see how to do this with NeRFs. Normally, from a single frame that we recorded, we would create a single example into our training dataset. However, this is a bit wasteful, as we can easily imagine what would happen if the car was turned slightly in either direction, or perhaps in a slightly different position in the lane. We can create a new trajectory from this position that merges back to the original trajectory in a physically plausible way. And then we can keep doing that for as many initial poses as we would like. So in this way, we can construct, from just one input image, we can construct hundreds additional training examples. Now let's look at the evaluation use case. Having a reliable set of metrics is critical for the iterative development of an ML system. For us, the simplest method of evaluating a model is using a video recorded previously by an expert during on-road testing. We can show an image to a model and ask it what it would do in this situation. Let's say, for this example, the model says, I'd turn a bit more to the right. So then we ask, okay, we turned a little bit to the right, and what would you do next? And then the model says, well, what does it look like right now? And this is where we have to terminate the test, because the original video that we recorded, the model did not turn to the right. It was driving straight. So we don't have the input that we need to generate the next action. This kind of test is called an open loop test, because the actions taken by the model do not affect the future state. There is no feedback loop. On the other hand, deploying a model on the road is the ultimate test, but it's an expensive manual process and very, very slow to do at scale. So ideally, we would want something in between, an automated closed-loop test. We still use a video of a previous run, except this time we turned it into a NeRF. When the model under test chooses an action, we can simulate where the car would end up using a physics model. We then render the novel state with NeRF. This creates a feedback loop. Model's actions affect the future state, hence the test is closed loop. Let's see what this looks like. We start by evaluating the model from the original initial pose. We can also generate a what-if scenario. What if the initial pose of the model was slightly perturbed, like here? We can also test what a different model would do in a similar condition. And finally, we can run this for hundreds initial positions at scale to generate reliable metrics. In order to fully automate such tests, we also need an automated termination condition, such as cross-track error against the expert trajectory, or perhaps intersection with the drivable area based on the semantic segmentation. Or finally, we could also do collision detection by querying the density of the radiance field. And in practice, we use a mixture of the three. Okay, so we have now seen how useful the NeRFs can be for self-driving cars and how they can be simply built from collections of images or videos. So all that's left is to launch a training job and watch the loss go down. Well, not so easy. NeRFs have a few serious problems for the AV application that we need to solve before we move to city scale. First, NeRFs require pixel-perfect localization for the camera poses in order to correctly register all images. Our lean sensor suite provides accurate localization required for driving, but may not reach the centimeter level precision required for picture registration. Secondly, we've discovered that NeRFs have scene size limit. We found that segments longer than 150 meters, for those segments, the quality starts to deteriorate quickly, or they become infeasible to train. And thirdly, the classic formula for NeRFs can only capture static scenes. If you go back to the Radiance field function, we see that there is no space for time dimension here, meaning it can only register scenes that do not change over time. However, for us, registering dynamic agents is quite important. There are methods emerging for capturing dynamic NeRFs. However, none of them seem to be suitable for our use case because they seem to require an extensive camera rig that captures pretty much all of the scene at the same time. We've been able to find some solutions to overcome those limitations. First, for localization, our solution is to use structure from motion. By solving structure from motion or another simultaneous localization and mapping problem, we can obtain camera poses directly from images. We choose to solve SFM directly implemented by CallMap, as it's a popular solution in NeRF community, and it lets us discover the camera parameters, intrinsics and extrinsics, of our entire camera rig at the same time. To solve the second problem, size limit, we split the city scale NeRF into multiple short segments with a small overlap. We seamlessly swap the NeRFs when we detect the simulation approaches the boundary. We streamline block NeRFs approach because we are only interested in stitching together the scenes that were recorded one after the other. We do not need to render from more than one NeRF at a time, as we don't deviate much from the original vehicle's path, and we stay relatively close to the ground. Where there might be small differences in appearance between the NeRFs, but since the segments were recorded consecutively, they will be no bigger than the frame-to-frame differences in exposure. And what we gain from this approach is that our solution allows us to train and use each NeRF independently, which is important for scaling the solution. And here on the video, you can see a run stitched together from 7 NeRFs, so about 700 meters in total, in length. And finally, for dynamic NeRF solution, we have found a powerful solution by mixing NeRFs and traditional rendering to add dynamic agents. Let's see what this looks like. We start from source video as previously, except now we use a segmentation model to separate the dynamic and static part of the scene. We can train the NeRF on the static part of the scene as previously, and for the dynamic part, we can use a depth model, a monodepth model, to create a point cloud, and then later turn this point cloud using a surface reconstruction algorithm into a mesh. A mesh we can now render using a traditional rendering pipeline, and we can also superimpose the dynamic part and the static part on the scene rendered via NeRF into one single image. And this method also allows us to edit time, so we can move the time backwards or forwards. This solution doesn't allow us to edit the scene to the extent as the solution presented, for example, in Panoptic Neural Fields paper. However, what we get in return is a smaller set of dependencies, just a segmentation and a depth model, and the ability to process each segment completely independently, which again will be important in the neural fleet pipeline design. So now let's see how do all those steps come together to build a city scale NeRF. First design decision that we made is that NeRFs are pre-computed rather than offered on demand. This removes a lot of moving parts from serving time and reduces latency. The first step is to split the driving data, our entire driving data corpus, into 100-meter long segments. After the segments are split, each of them can be processed independently, making it an embarrassingly parallelizable problem. And this is what lets us take it to the city scale, because with this way of framing the problem, we can just as easily train 100 NeRFs, 1,000 NeRFs, 100,000 or 1,000,000 NeRFs. Now, the consequent steps in the pipeline are segmentation labeling for dynamic NeRFs, call map for camera localization, and finally training the NeRF and storing it on disk. Each stage of the pipeline is independently versioned and cached, which enables independent iteration. And additionally, stages report the metrics, their quality metrics, to a metrics database. And based on those metrics, we can either retry some steps or mark certain stages as unusable and abort quickly. And now to give you some implementation details. We run our pipeline on Spark, an open source distributed computing framework designed for processing large amounts of data. With Spark, we get automated scheduling, fault tolerance, retries, error reporting, etc. We run our Spark pipeline on Azure Kubernetes service, which gives us freedom of choice for underlying nodes. And how can we train millions of NeRFs in a short time? We run our pipeline on a heterogeneous CPU and GPU cluster that includes 900 nodes equipped with NVIDIA T4 GPUs. To further optimize the cost, we use Spark's resource profiles to optimize node usage. For example, our call map step does not require a GPU, which means we can redirect it to cheaper CPU-only machines to save some money. We can further optimize the cost by leveraging spot instances because Spark provides us with fault tolerance. And finally, we save the results on disk to Azure Blob Storage and download them for the inference engine when needed. Wave is interested in building a global product. We are developing a self-driving solution that can scale worldwide, and so it's important that everything we do pushes us towards the scale, like the neural fleets we discussed today. Thank you for listening. At Wave, we take many approaches to simulation and scaling self-driving. Here are some resources that I mentioned during the talk. If you found it interesting, I'd like to encourage you to check out our engineering blog and other channels. Thank you.